Hi, my name is Sam Matlow. I'm a graduate student at UCF, University of Central Florida. And today I'm doing a presentation about a three coloring problem. It is, a presentation for one of my classes in this semester. Is actually for design and analysis of algorithms in fall 2021. So what is the three coloring problem? Um, what I'm going to start the presentation with is actually explain what the three coloring problem actually is. And throughout the presentation, I'm going to try to prove that the three coloring problem is actually an NP-complete problem. And therefore, kind of talk about the NP-complete problem, why is it considered as an NP-complete and so forth. And we're going to go from there to dive into different topics until, kind of prove that the three coloring problem is actually an NP-complete. All right, so first thing first, what is an NP-complete problems? Well, an NP-complete problems are problems that we actually can design an algorithm that solves the problem in a polynomial time. Therefore, these kind of problems are actually taking a long time until we guess or get a working solution for the problem. And usually the only solution for these kind of problems is a brute force solution where we have to go through all the possibilities until we get the answer to the problem. And why is it called NP complete? Why is it NP? So one of the character for problems that fall under this category is they're hard to solve, but at the same time, once we guess or get a solution, an answer, it's very easy to verify. Usually it takes a polynomial time to verify if the answer that we have gotten from an algorithm is actually a valid one or not. All right, so what is the three coloring problem? The three coloring problem is a graph problem. Let me draw a graph diagram really quickly, and then I'll explain. So let's assume we have 5 vertices in a graph, and they're connected as follows. And what we want to do is to assign a color in each vertex in a way that any adjacent vertices can't have the same color. So let's assume we have 3 colors that we want to color the vertices in this diagram. And these colors are, let's say, green, blue, and red. So let's go ahead and start with the top vertex, and let's go ahead and assign it the color green. And therefore, if I assign the color green to the top vertex, I can't assign the color green in this vertex, nor I can assign green in this vertex either, because both of these vertices are actually connected to the green vertex at the top. So I have only 2 other colors that I can assign this vertex with, either blue or red. So I'm going to go ahead and select blue here. And so eventually this vertex must have a color of red in order to fulfill the requirement here. And therefore, if we continue in the same way, assign colors to the other vertices, then we might be able to get something similar to this. And so that's actually the three coloring problem of a graph. So basically the problem is we're trying to give or assign three colors to vertices in a graph in a way that no adjacent vertices can have the same color. Although it sounds really easy, but ironically, this problem is actually a hard problem that we can't solve in a polynomial time. And it is actually an NP complete. All right. So, well, how can we prove that this problem is actually an NP complete? So one of the approaches that usually mathematicians use is actually rely on a different problem, and from the other problem derive to this or make some relation to the problem they're studying, and then they kind of make a conclusion from there. And this problem and this issue is no different. So what we're going to do, we're going to rely on another algorithm, another problem that we know and we have proven that the other problem is an NP complete. And that problem that we're going to try to use and rely for this, for the process of proving this problem as an NP complete is called the SAT problem. And I'm going to explain what the SAT problem, and by the way, SAT problem is abbreviation for the satisfiability problem. And I'm going to explain, like I said, what the satisfiability problem in a bit, but here is the approach. So I'm going to start from the satisfiability problem that we already know, that we already have proven that this problem, the satisfiability problem, is an NP complete, and I'm going to try to convert it in a smart way, reduce it to make it similar to the three coloring problem, kind of reduce it from the SAT problem to the three coloring problem. And if I would be able to do that, then I can say that the three coloring problem is an NP complete. Because if it is not NP complete, then I can solve the three coloring problem in polynomial time. And therefore, I can also solve the problem that I derived the three coloring problem from, which is the SAT, the satisfiability problem, in a polynomial time. And that's a contradiction to what we already know. So this is the approach that we're going to take to conclude that the three coloring problem is an NP complete. So first thing first, what is the SAT? What is the satisfiability problem? So let's draw something that help us understand what the satisfiability problem is. All right, so the satisfiability problem is like this. It's a logic problem, and basically we have some sort of a circuit, a box full of logic operations, and we have on one side many inputs, I1, I2, I3, I4, many inputs, and we have one output. And the problem states that we need to find an algorithm that assigns I1, I2, I3 with values, true or false, in a way that we can get a logic true as an output. Sounds simple, right? Or easy. But matter of fact is, this is an NP complete. We can't solve this problem in a polynomial time. It is an NP complete, or falls under the NP problems, because if we if we guessed some inputs and we wanted to verify if these inputs are correct or valid, as we can see, it's just a logic circuit with a bunch of logic operations or not operation and so forth. So it's really easy to just plug in these inputs into some into the computer, and we can get and calculate the output. But again, as finding the assignments for each input in order to get the output to become a true is an NP complete. All right. So from this idea, from this satisfiability problem, what we're going to try to do, if we could, we're going to try to convert some, the logic operations to something that mimic the graph problem somehow. So let's think about something. Let me draw this diagram really quickly, and then we'll talk further about it. So if we have all right. So we're talking about coloring the graph, right? And we need to just kind of keeping in mind that when we assign color to vertices, no adjacent vertices will have the same color. So what if the color means something? What if the green maybe means true? And what if the blue means false? Matter of fact, let's go ahead and assume green means true and blue means false. And we can say red means, anything else, neutral, right? Let's call it N. And how about if we try to color these three vertices? So if we color them, if we want to color them, putting the requirement in mind, then we're eventually going to say, or to assign the vertices as in maybe, so let's put R instead of N. And let's put here blue, put here green, right? And to kind of make the analogy with the logic circuit, we're going to just denote underneath that green is true, so T. For blue is false, and for red as in neutral. All right. So, and also pay attention to the fact that from R, from the neutral, we actually connected, so we have the other two vertices right here, and the R, the vertex at the top, is connected to the first to the top vertex on the other side, and R also, or the neutral vertex, is connected to the vertex at the bottom on the other side. All right. So therefore, the way that the graph is structured and connected, if we assign green in here, what is the color that we must assign to the vertex at the bottom? If we assign green, so this vertex can get green, and it also can get red or neutral. So the only option we're left with is actually blue. And if we selected blue here at the top, then we can't get blue at the bottom, and we can't get red, but we can only assign, this is the only option that we can have assigned to the bottom vertex is actually green. What is that telling us? So if we have green at the top, then we will have blue. Or if we have blue at the top, then we're going to have green at the bottom. So let's kind of switch it just a little bit and kind of show or replace the colors with true and false. So if we have green, true, then this vertex is going to have false. If we have false, then this vertex is going to have true. Oh, what is that? This is a NOT operation. This is actually functioning exactly like a NOT logic operation. Therefore, any NOT operation, like for example here, I can actually take it out and replace it with this diagram. So this is going to be my input, for example, and this is going to be my output. So that's actually the first step to convert from the satisfiable problem to the three-colored problem, replacing the logic inside this box to a graph diagram. Well, how about the OR? So if we get the OR, or have like a diagram that represents the OR functionality, then we're pretty much, kind of done. Okay, so let's go ahead and try do that. That's going to be interesting, really. All right. So if we have this graph like this, and this is little graphs or little vertex. Let's say this is blue, this is green, this is red, and it's connected in here, this is connected in here. All right. And we have another two connections from here to here, and from here to here. All right. So this diagram, believe it or not, is actually behaves like an OR function, like an OR logic. This being the output, and these the inputs, I1, I2. So let's go ahead and try to understand how this graph diagram is actually mimicking the OR function, or the logic OR function in a logic circuit. So we have these three vertices, and we have the inputs. So let's assume that I1 is going to be green. That is true. And I2 is going to be blue for false. Right? So if green, or if true or false, then the output we're expecting is actually to be true as well. So the expected output is going to be true. Let's go ahead and try to figure out and prove that. So this is green, this is blue. Therefore, this has to be red, right? Because this vertex is connected to both vertices. So this vertex can be blue and can be green. The only color left is actually blue, following the three color assignments. All right, well, if this is red and this vertex is green, then this vertex that connects to the red vertex and the green vertex from the other side has to be blue, must be blue. All right. So if this is blue, and which is connected to the vertex that we're considering as an output, and at the same time the output vertex is also connected to a red vertex, so we have blue and we have red, then this must be assigned a green color. Right? Oh, hold on. The green means it's true, right? Green equals true. So if we have true or false, we have the output as in true. So this diagram so far is actually working as an OR, as a logic OR. Well, now how about if we have I1 and I2 both assigned blue, which is false? Let's see how this diagram behaves. So if this is blue, that means it's false, and this is false as well. So the expected output is actually going to be false, right? Let's go ahead and take this color out from this vertex from the previous example. All right, so let's rethink the colors again. So this one is blue, this one is a blue. So this vertex has to be either green or red, right? So let's assign red, right? I like red. So let's assign red in here. Well, if this red, then this guy has to be green, because it is connected to a red color from one side and blue color from the other side, from the bottom. So it has to be green. Oh, wait. So if we have red and green connected to the top vertex, then the only color that the top vertex can have is actually blue. Oh, wait. So if we colored blue, or if we assign the color blue to the top vertex, to the output vertex, blue means false. Oh, so the condition for the logic OR is also here applicable. It's actually, this diagram is, mimicking the function of the logic OR. That's great. That's great news to us. So then what happens is, now, for any OR, logic OR in the logic circuit in this box, we can take this graph and replace the OR function from here, or the OR function in here, replace it with this diagram, with this graph, assigning, as I mentioned here, the inputs to these, like any inputs from here, or any inputs to the logic OR, assigning to or connect them to these vertices, and the output of the logic OR is going to be this vertex at the top. So we have the logic OR being replaced with a graph diagram. We have the NOT function, or the logic NOT, replaced also with another graph diagram. So basically, we can replace whatever in the logic circuit with a graph diagram that mimics or that follows the three coloring in it. All right, so then if we replace everything in here with graph diagrams, and then we have inputs that we need to figure out in order to get, an output of true, then we have to ask the question is, if just assume that there is such, an algorithm that solves the three-color problem in a polynomial time, then definitely we can solve the satisfiable problem in a polynomial time as well. Which is a contradiction, as I mentioned before, because the satisfiability problem has already proven that it is an NP-complete and it cannot be solved in a polynomial time. Therefore, the three-coloring problem is an NP-complete. And that actually concludes the presentation about the three-coloring problem. Thank you very much.